So this paper is again on an important topic and is very closely related to the last podcast where we looked at how the Pacific climate change signal is emerging from the background of internal variability dominated by the interdecadal Pacific Oscillation. And we looked at the wind patterns, IPO, PCC, Pacific climate change, and how the ocean has responded. And we already looked at some figures, vertical profiles, and the terms that have been driving the heat content change, sea surface height change, and so on. This paper goes into more details of the same things, and the ocean part of it, and looks at the dynamics of what is causing historic subsurface cooling in the tropical Pacific, which is obviously a very critical region, as we said in the previous podcast as well as before, in terms of determining the global response to anthropogenic forcing, right? So we'll look at the equations that I was a bit lazy about in the last podcast, and I'll still be brief, but at least we'll get the main points across, I hope. Understanding how the tropical Pacific responds to rising greenhouse gases in recent decades is of paramount importance given its central role in global climate systems. Extensive research has explored the long-term trends of tropical Pacific sea surface temperatures and the overlying atmosphere, yet the historical change in the upper ocean has received far less attention. Here we represent compelling evidence of a prominent subsurface cooling pattern along the thermocline in the central to eastern tropical Pacific since 1958, which approximately coincides with the emergence of the Pacific climate change signal that we talked about in the previous podcast. This subsurface cooling has been argued to be contributing to the observed cooling or lack of warming in the equatorial cold tongue SST. We further demonstrate that different mechanisms are responsible for different parts of the subsurface cooling in the central to eastern equatorial Pacific and the southeastern of equatorial Pacific, where zonal wind stress strengthens. A pronounced subsurface cooling trend emerges just above the thermocline that is closely tied to increased Ekman pumping, so wind stress curls and Ekman pumping. In the eastern equatorial Pacific, where zonal wind stress weakens, the westward surface current and eastward equatorial undercurrent weaken as well, resulting in reduced vertical current shear and increased ocean stability, which suppresses vertical mixing and leads to local cooling. So very different processes. We conclude that the historical subsurface cooling is primarily linked to dynamical adjustments of the ocean currents to tropical surface wind stress change. So we did look at the vertical profiles or the meridional profiles of the heat content in the previous podcast. We'll look at a bit more detail here. So what are they trying to do? In this study, we focus on how the upper ocean temperatures in the tropical Pacific have changed over the past 6 decades during a rapid increase in GHGs, greenhouse gases. This paper is structured as follows, so I won't go into the details there. So let's just jump into some results. This is looking at ORAS-5 again, which is the ocean reanalysis product, and you are looking at meridional mean deep tropical 5 south 5 north in the XZ plane, so depth versus longitude. Zonal mean, so B is the zonal mean in meridional section, zonally averaged the date line to 120 degree west in the YZ plane, so depth versus latitudes, and other observed only and reanalysis temperature trend in XZ again, and other observation only and reanalysis in the YZ. So let's read completely the caption. So zonal mean in B, these are trends, remember, for ORAS-5. Black and red lines indicate the thermocline depth in P1, period 1, 1958 to 77, and P2, 2003 to 2022 for ORAS-5. Dots in A and B indicate trend values with statistical significance. C and D are same as A and B, but for the composite of other reanalysis and observation only data sets, including SODA, EN4 and ISHI. So they are just trying to say that the results are robust. Magnitudes change. Obviously, this is much more robust, but still above the thermocline, and still the same pattern. The magnitudes, whatever, are different. Okay, so black and red lines indicate thermocline depth for the two periods, as I said. Whereas 5 temperature trends, shading and contour in degree C per decade at the surface: 50 meters, 100 meters, 200 meters, and 300 meters, with dots indicating statistical significance. So not significant here in SST, but significant in these regions. Whereas 50 meter trend, okay, significant, 100 meters, so basically the subsurface cooling is not as strong here, statistically speaking, not so significant. At 50 meters, already more extensive, meridionally broad, still meridionally stuck in the 100 meter depth, but you can see the pattern is somewhat different here and extends pretty much over the entire zonal extent, and at 300 meter and it weakens again. So that's consistent with where the major maximum loading is. So you can think of it as essentially a shoaling of the thermocline, or the cooling going down to 200 meters. I don't want to say shoaling of the thermocline, because then you will have to make sure that the thermocline is lifting and not just the cooling is above the thermocline itself. So some details. So the heat budget equation, which I alluded to at the end of the last podcast, each grid point you have temperature trend with zonal, meridional, vertical advections, and a residual term you always end up with because budgets don't close. And they split the advection into anomalous currents in the zonal, meridional, and vertical directions, and mean currents, so climatology and anomalies, and the same thing for temperature, which is a standard way of doing things. Advection of heat content anomalies with anomalous currents, and vice versa, advection of the mean heat content, let's say, with did I say the same thing? So climatology, anomaly, climatology, you get the idea. Okay, so here are the trends from another different reanalysis products. Meridional, so 5 south, 5 north XZ plane, and zonal. Zonal extend from dateline to 120 west in the YZ plane. Subsurface temperature trends for degree C, as degree C per decade for EN4. Black and red lines again indicate thermocline depth in P1, P2. They are just mean depths, not trends. Dots indicate trend values exceeding 95%. C and D are same as A and B, but for another product, EC, ENF are the same, but soda. So basically they are all consistent with each other in the zonal direction and the meridional direction, as we said before, in terms of the trend over the period that we are looking at. If you want to get into a bit more detail, we find the average of heat budget terms in the most recent, so the P2 period 2003 to 2022, when the temperature changed, and subtract the reference state. So some details there in terms of P2 minus P1 period for the advection term and the residual terms. And from equation 2, this is how you define the average over those periods. So you take the anomalous and the residual terms here. So anomalous advection of mean heat content for the two periods, and anomalous vertical advection of the heat content, mean heat content in the two periods, and the residuals. Why do they do this? Basically, they are trying to understand the similar to the previous podcast, how the dynamics, the trends versus internal variability are behaving. Ekman transport, in the previous podcast, some of you may have wondered how come they show Ekman pumping Ekman transport on the equator, but that's because they have added a friction term which makes sure that the bottom doesn't go to 0. In general, when you do curl tau over f or so, you get no Ekman transport definition on the equator, but this is zonal and meridional Ekman transport as well as vertical Ekman transport, so it's related obviously to the wind stress curl. So you are trying to separate the thermocline heaving term and the processes of zonal advection, even though thermocline heaving is associated with divergences and convergences as well, right? So meridional mean 5 south 5 north and zonal mean the central part of, so you are looking at the sum of the advection change. You can see the contrasts here, and sum of the YZ in the central equatorial Pacific and eastern equatorial Pacific. Okay, so you can see how the changes have occurred. So that's A and B, and you have what did I do with C? Yeah, B and C are here, sorry. So meridional mean and zonal mean for the central part of the central to eastern Pacific, CEP, which is here, central to eastern, and these are the east part, so that is EEP of the sum of climatological advection terms and the change P2 minus P1 in the sum of the climatological advection terms. So you are trying to see how the ocean dynamics have changed for the recent period. D2F as in A to C, but for zonal advection and for meridional advection, but for verticals. I'm just repeating myself. So the sum terms are here: meridional advection, zonal advection, and vertical advection terms. They have all changed, and you just want to basically put the details on how the winds have changed, how the ocean response has changed, and the winds have changed in magnitude and in the distribution and the wind stress curl, right? And in this figure, we are looking at zonal current changes in the XY plane and looking at the meridional plane, so latitudes here for central to eastern Pacific and eastern equatorial Pacific. So you can basically think about the meridional cells, but changes in the zonal currents, which are obviously related to each other. You can see that what we said before still holds in terms of how the wind changes are manifest in the zonal currents and meridional currents, both in the zonal plane and in the meridional plane. Obviously, the meridional currents tend to be complicated. You can, because of the upwelling, and the magnitudes also tend to be very different. You can see it's here in 0.01 scale, whereas here it's 0.1 scale in meters per second. W will be even smaller, it's in meters per day. So you have to be sure that you are noting the units. W is always in meters per day. So this is the W change in the zonal direction and in the meridional direction. So I'm being lazy again, but decomposition of the dynamical contributions of, to the cooling in degrees C per month, that should be, per decade, I suspect. So zonal advection terms for the central to eastern Pacific and eastern equatorial Pacific here. Zonal contributing the most in terms of the mean heat content being advected by the anomalous current and the anomalous advection of anomalous heat. Okay, so those two terms, but also the climatological currents advecting anomalous heat is also contributing, whereas the meridional contributions are low. In the vertical, anomalous vertical advection of the mean state is the dominant term, even though there is a bit of contribution from anomalous advection of anomalous heat content. Okay, so for the eastern equatorial Pacific, you can see it's quite different. The magnitudes are the same, so the contributions are positive for the anomalous currents, climatological heat temperature, let's say, and anomalous temperatures, whereas the negative contribution cooling term comes from mean currents advecting anomalous temperatures, and meridional is larger than here than in the central equatorial Pacific because the divergence term is very strong as well, and vertical advection is significantly smaller, but they are making positive contributions, so they are actually warming in that sense. Okay, so being very brief, here we are looking again at each term. So anomalous advection of mean temperatures, warming effect. In the meridional direction, you can see the equatorial versus off equatorial in the central versus the eastern. Okay, similar patterns, but loading is different, asymmetry, southern contribution, we know. You remember the asymmetry of the cooling pattern is shifted towards the southeastern Pacific, which is being captured here, and the equatorial term is stronger, and here you have mean advection of the anomalous temperatures, a little bit noisy but still contributing to cooling here. Similarly, meridional patterns and anomalous advection of anomalous temperatures changing is also contributing to warming. So this is a mixed bag, warming, but this dominates obviously, and the meridional terms also determine what comes in, right? So this is the meridional term of the anomalous zonal advection of the temperature anomaly. So there are similar terms for vertical. Now you can see contribution to anomalous vertical advection of the mean temperatures is strong cooling, seen also here. What is seen here is consistent with what is happening with the zonal advection. They all have to be consistent, right? You have to diverge, do vertical thing, right? This is the vertical mean versus temperature advection, cooling in the meridional, and this is the anomalous vertical advection of anomalous temperatures, very strong cooling. Okay, so those have to be consistent with these terms as well in the central and eastern Pacific. These are the meridional terms. So this is figure 6, 7, 8, and they have separated them because they are looking at each term anomalous advection of mean and mean advection of anomalous and anomalous advection of anomalous. So meridional is weaker, but still obviously contributing to warming or cooling depending on where you are in the central or eastern Pacific. Okay, so the changes in the period P2 and P1 2003 to 2022 and before in the surface wind stress vectors and its magnitude shown in meters per second, you can see what's happening. We already talked about this in the superposition of IPO and PCC, but we are not separating that here. So surface wind stress change is very strong here, and it is weaker, but here, as you can see, with the negative wind speeds and Ekman transport and pumping change. So you can see divergence here, not so strong here, but strong southward advection and some northward advection here. So you can take these for what they are. This is in meter per second Ekman pumping velocity. Again, on the equator they can compute by adding a friction term. So this is better because if you put a blank because you are using the simple formula without friction, then you get a horrible figure. But this tells you about the contribution of the Ekman advection and divergence to the subsurface cooling along with the zonal, meridional and vertical advection terms. Okay, so these are the profile changes. You can see equatorial zonal current anomaly. We talked about the equatorial undercurrent changes. So this is the observed euclimatology. This is basically comparing the data versus the reanalysis products to make sure that we are how far off we are. Okay, so vertical profile of the climatology of zonal current in the P1 in meter per second and the change in P2 minus P1 in B. Okay, so in the zonal current averaged over the equatorial Pacific, eastern Pacific, so that is on the equator 145 to 110 west, C and D are same as B, but for the vertical velocity change related and thermocline depth change related zonal current average. A little bit complicated, but basically they are trying to separate the dynamics of the central and eastern Pacific and the processes that are creating above thermocline cooling and above thermocline cooling in the east versus the center, and you can see the differences here. So the change in vertical shear of zonal current du dz squared averaged over 1 south 1 north, change in gradient of Richardson number, which is a measure of turbulence which induces a mixing in models typically and indicates dynamic instability. So vertical shear, and basically think of it as energy available for vertical mixing. Okay, so P2 minus P1. These are kind of complicated figures, so I'm going to be very brief and lazy about this, but basically they all add up to the conclusion discussion in terms of what the processes are, which is easier to read. If you want more details of the calculations, you need to go back to the paper, right? In this study, we investigated the characteristics of the historical subsurface temperature trend in the tropical Pacific and underlying dynamics, primarily based on ORAS-5 data. We show that a subsurface cooling pattern along the thermocline is evident in the central to eastern Pacific since 1958, which is robust across another reanalysis and observation only data. We further established that this cooling is primarily linked to the dynamical adjustment of ocean currents in response to tropical surface wind stress changes through changes in the Ekman pumping and vertical mixing. In the central equatorial Pacific and in the southeastern of equatorial Pacific, where zonal wind stress exhibits a strengthening trend, a pronounced subsurface cooling trend emerges just above the thermocline that is closely tied to the strengthening of the Ekman pumping. In the eastern equatorial Pacific, where zonal wind stress weakens, the westward surface current and eastward equatorial undercurrent weaken as well, resulting in reduced vertical shear and increased ocean stability, which suppresses vertical mixing and leads to local cooling. So you are just lifting the water and not mixing it away. Okay, so remember the southeast Pacific is got a direct entry into the deep tropical Pacific, as opposed to the northern part where there is a ITCZ, the potential vorticity barrier, and so on. So the wind dynamics are going from southeastern Pacific into the central Pacific, whereas the eastern Pacific around the equator is behaving differently because of the dynamical processes there. While we have shown how the changes in the upper tropical Pacific Ocean circulation and thermal structure can be explained as a response to the changes in surface wind stress changes respond to changes in SSTs that are influenced by the changes in the upper tropical Pacific Ocean. So there is obviously a feedback. Seeger et al. Argued that the thermocline cooling and shoaling were keys to explaining the trend toward an enhanced zonal SST gradient across the equatorial Pacific, and that the wind response to that was to strengthen the southeast trades and northeast trades over the west Pacific, much as observed. So that is this part here. So extent of the trade winds is penetrating further west, as is obvious in the figure. Current evidence strongly suggests that the coupled tropical Pacific atmosphere upper ocean system has been evolving over the past 6 decades toward a state characterized by upper thermocline cooling and enhanced equatorial SST gradient and strengthened trades, so the Walker cell. Note that it does not rule out other possibilities beyond the ocean dynamical thermostat mechanism, as surface wind stress can also be influenced by remote forcings from the extratropical forcings, for example, further, or from the Indian and tropical Indian and the Atlantic as well. Future work needs to determine whether these trends are a tropical Pacific response to anthropogenic effects, such as rising greenhouse gases, ozone depletion, and non-monotonic aerosol emissions, or whether they come from internal multi-decadal variability, the IPO that we talked about before, or are themselves responding to changes elsewhere, such as over the southern Ocean and Southeast Pacific. Indian Ocean is not mentioned, but many people have argued that the heat uptake in the Pacific is being affected by the Indian Ocean warming as well. Okay. Lastly, it is important to acknowledge that although a consistent cooling trend is identified across various ocean reanalysis and observational only data sets, further efforts are necessary to narrow down the uncertainty surrounding this cooling feature and its underlying mechanism. The beautiful bird that's not making any noise. As extensively discussed in previous studies, sorry I mucked up the patching here, one should be cautious when analyzing and interpreting the long-term trends in the observation given various issues related to the data quality. This is particularly relevant for ocean data, which are often poorly observed in earlier periods, leading to observations that may be insufficient for accurately determining oceanic diagnostic quantities. The ocean reanalysis data derived from ocean model outputs are driven by presumably more reliable atmospheric data as boundary conditions and constrained by in situ information, but inevitably suffer from the uncertainty in the atmospheric forcing data. It's a complicated picture, but you have to do the best you can, and you have to look for consistencies. Winds, SSTs, subsurface, thermocline, heat content, etc. For example, the ocean reanalysis, or S5, uses different generations of atmospheric reanalysis datasets as boundary conditions across time, thereby introducing potential errors related to atmospheric reanalysis uncertainties, including discontinuities in data quality. So if you want to make a long ocean reanalysis where you are integrating an ocean model and inserting ocean data, then you need atmospheric forcing in terms of winds and surface fluxes, and consistent forcing may not be available, so people used two different products and they worry about the smoothness, continuity, differences, biases, uncertainties, and yet you are left with something in the ocean reanalysis. Okay, reconciling the differences among different observational and analysis datasets poses a continuing challenge for the climate community, but we must keep doing the best we can with what we have and focus on the important science questions, especially in terms of where we are headed, because tropical Pacific is really the pacemaker for global warming and the coupled ocean atmosphere climate response. Okay, so see you in the next topic.